All right, so here's what I got, and hopefully you got something similar. I want to also point out that you can, it's really tedious and obnoxious to do these things, but you can simplify the work by looking for patterns. So for example, as long as I notice everywhere on the line y equals x, whenever y is equal to x, this slope is going to be -1. So once I notice that, go on to all the y equals x lines, all the y equals x points. That's, where's the line y equals x? It's this point, this point, this point, this point, this point, this point. All right, well, those points are all going to have slope 1. So I can, line up carefully. It's a little hard to do with the camera there. So we'll do it like that. Okay, so line up and just make a nice, that one was a little too big. We want to make them smallish. And just put slope 1s there. Now I'm skipping this one because that one's actually undefined. And we're going to talk about the undefined ones, and it's weird. All right, so there we go. And then the other thing that you might notice is when x is equal to -y, so on the y equals -x line, all the slopes are going to be +1. Here's our y equals -x line going like this. So look for patterns like this, because look how much faster that makes the work if you recognize patterns. So I'm going to do a nice slope 1 right there, right there, right there. I'm going to skip the undefined one right there, right there. And then I got all those. All right, what else can I notice? I can notice whenever the x-coordinate is 0, the slope's going to be 0. So that means all the slopes on the y-axis, this one, this one, this one, this one, this one, this one, not the undefined one, they're all going to have horizontal slopes. So slope 0, slope 0, slope 0. So, I'm doing it less carefully now than I did over here. But, you can still see it's not bad. And what else? Whenever the y is equal to 0, the slope is undefined. So y is equal to 0 here, 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 here. So when we have undefined slope, we have a vertical line, right? So we have vertical lines here, here. All right, I think that one in the middle is a little different, though, so we'll talk about that one. All right. I was trying to avoid this kind of smudgy thing. It's like you should really do this with a pencil or a different kind of pen that dries quicker. All right. So if you notice what shapes we're generating here, what these slope fields are really about is flow. They're used a lot in fluid dynamics. Why is fluid dynamics important? Because climatology is nothing but fluid dynamics. Why is climatology important? Because if we don't get it right, we're all going to die, and I mean everybody. So we got to get the climatology right. A lot of very bright people are working on it, and they use a lot of slope fields, and you can actually look at a lot of weather modeling. It's all slope fields. Look at a wind map of the continent. You'll see nothing but slope fields. All right, so the patterns are circular, right? So when I have these undefined points where the slope is undefined, so that little slope is vertical, all right? But 0 over 0 is a different kind of undefined. So if I have a constant over 0, I'm going to have a vertical slope. All right, but 0 over 0 is sort of more weirdly undefined. You have no slope at all. So what I usually put is a point there. And you can see that it still sort of follows the idea of circularity. That's what that's really about. All right, what else can you do in terms of patterns? Not much else. I mean, the rest of it is noticing that this is going to be, I don't know, do I really have anything for this? We fill in the rest of the slopes. But look how much of it we got just by using patterns. And then you've got a finite, you've only got 1, 2, 3, 4, 5, 6 in each quadrant left to do. So that's 24 points left to do, and we've already done some of them. All right, so we get this. That's what we get once we fill those in. And I'm just saying, take advantage of patterns. The next one we're going to do is going to have a lot of patterns in it. Now, looking at this and thinking about flow, what kind of shapes do you see here? What kind of shapes will follow those slopes? All right, if you said circles, that's because these are circular slopes. All right, these are the slopes that a circle has. But anywhere you start, if you follow, you have to think about following along the slopes. So if you think of these slopes as constituting a fluid flow and you're following along it, like these are ocean currents and you're drifting along them, or they're air currents and you're a weather balloon. All right, circular, you're going to go in a circle. So what we see here is a lot of different circles of varying radius. Now I'm for convenience sake, only putting in the whole number radii. But of course, there are many other circles. There are irrational radii, rational radii, lots of different real numbered radii. So what we have is a bunch of circles, but they all are centered at 0. All right. Now, what do you know about circles? In terms of an equation? What do you know? What's the equation for a circle centered at the origin? What is the equation for a circle centered at the origin? It's x squared plus y squared equals r squared. Now look at the equation we started with. Yeah. The slope field told us we had a geometric pattern, a graphical pattern, that has an equation that in fact leads us back to our original place where we got this derivative. So could you reverse this? The first thing to do is draw a picture and see what kind of functions match the picture. Of course, there are more analytic ways to do it, but it's very important to understand this bit here. Now, but here's the problem. If all I know is the derivative, I have infinitely many circles, just like if all I knew was dy dx equals, let's say, x, all right, then I know that y equals x squared over 2 plus c. So what I would know is I have parabolas, but there are infinitely many parabolas that solve that also can also be called a differential equation. So if all I know is the derivative, remember, when I integrate up, I have to restore lost information. So when I did the dy dx, I lost this piece of information. I lost what the radius was, because no matter what the radius was, the derivative of that was going to be 0. So as soon as we did the derivative, we come down here with less information than we started. So if we want to go back up, we are going to have to supply information. So we must supply information to restore the original equation. Supply information. How do we supply information? Well, in our earlier examples, when we were doing accumulation problems, you had to know a value at a particular time. Well, that's the same thing here. If I want to recall the original equation, then I have to know at least one point in the circle. I don't have to know all the points in the circle, just one of them. So if I was told that the point 0, 2 was on the circle, so if I had this differential equation, so I have now dy dx equals negative x over y, and if I know that the point 2, 0 is on the function, I guess I'll say. It's really not a function. I don't want to get too confused with that. All right. If I know that 2, 0 is a point on the graph that I'm looking for, then there's only one circle that matches that one particular point. All right. So what we have here is called a general solution. This slope field gives us all of the possible solutions to this differential equation. If I want to know a particular solution, I can sketch the particular solution through, or we can sometimes say containing, the point 2, 0. All right, so that's the idea, is if we have a differential equation, we can construct a slope field. The slope field gives us infinitely many solutions. If we have one particular solution, then we can identify the specific equation that came from. All right, so we'll look at some more examples of that next.